Hello, and welcome to MC312 Thermal Fluid Systems 2. Today we'll be talking about ideal gas relationships, building upon the fundamentals of ideal gas that we learned back in MC311. In this two-video series, we'll be developing equations to calculate the entropy change of an ideal gas. We'll be developing equations for entropy change with constant specific heats or variable specific heats. Then lastly, we'll close it out with developing the relationships for an isotropic process of an ideal gas at both constant specific heats and variable specific heats. Be using the Gibbs equations, our knowledge of how internal energy and enthalpy are only a function of temperature of an ideal gas, and also utilizing the ideal gas equation of state. Hopefully most of these are familiar to you from MC311, but do not worry, throughout the course of this first video, we'll be doing a good review and as we develop our equations to calculate our entropy change. So let's get after it. Of course, we need our roadmap to success for today. So let's go over our lesson objectives. First, we're going to apply the ideal gas equation of state to systems. It'll be throughout the course of this first video. Second, we'll be determine the entropy change of an ideal gas that undergoes a process. So that'll be our new concept that we'll develop and introduce that's different from what we talked about in MC311. And lastly, we're going to apply the isotropic relations to an ideal gas undergoing isotropic process. So that's where we're going to develop our isotropic relations of an ideal gas for both a constant specific heat assumption or a variable specific heat assumption. So first, before we get into the review, I'm going to show you a short video here. And this professor, this scientist, does a good job of talking about the ideal gas. And hopefully this will be a good little thought-provoking exercise as we get prepared for today's lesson. And as a reminder, please have your textbook open to Chapter 6, our reading for today, the RDC handy, as well as your reference manual handy. Thank you.
Here at Crash Course, generally like to be very safe. This is a little bit overkill here. I put a little bit of water into this soda can, and now I'm boiling it. So instead of atmospheric gas in this can right now, there's water vapor, and it's hot, and all the molecules are zipping around like crazy. We pick it up, and we plop it down inside of that. Oh! And it crushes itself. So what just happened there? Well, let's see what the gas law can tell us. So which of these things are changing? Starting on the right-hand side, R is constant, so that can't change. The temperature of the gas, though, that definitely changed. It drops like mad when it's exposed to the ice water. N is decreasing too, as water vapor is condensing into liquid water. It thus disappears from the gas phase, so the net result on the right-hand side is a decrease, and that means the left-hand side has to have a net decrease too. So on to the left-hand side, the pressure does indeed drop because the lower temperature makes the molecules move more slowly, thus bumping into the sides of the can a lot less than before. And volume drops too, but not quite for the reason you might think. It's really that the pressure inside the can goes so low that the pressure outside the can, the atmospheric pressure, literally crushes the can. Now I understand that you probably don't think this is as cool as I do, but understanding the physical reality of atoms and molecules smacking into things is a special kind of beautiful for me. It's also pretty cool that if you know any 3 things about a gas, you can figure out the 4th using the ideal gas law. Of course, not all gases behave ideally, and all gases deviate from the law at low temperatures or high pressures, but we'll save that discussion for a later episode.
Okay, great. So he brought up a lot of good points there. It is important to note that the ideal gas equation of state that he showed in his video is the ideal gas equation of state expressed on a molar basis, but you remember from 311 that we use the ideal gas equation of state on a mass basis. You'll find this on your MC312 reference sheet under the ideal gas block. He also brought up that not all gases can be assumed to be an ideal gas, but if we have a gas that's at low enough pressure or high enough temperature, we can model as an ideal gas. That's because we don't have the interaction of the molecules at the low pressure, that they're spaced far enough apart that they do not introduce a large error, whereas at a high temperature, the rapid movement of the molecules can overcome the forces of the attraction between the two, between the molecules, and then therefore the ideal gas model has low error and we can model it as such. All right, so that's a good thought-provoking video there and to get us into the mindset of ideal gas. So, all right, continue with our review here. Let's look at some topics that were introduced in MC311. First, we have our ideal gas equation of state. Here, equation 1.42, and this is the mass basis form of our ideal gas equation, where R bar and uppercase M are our universal gas constant and molecular weight respectively. And reminder that pressure and temperature must be in the absolute scale. A little foot stomp moment there, so please do not make that mistake. All right, moving on, we have our Gibbs equations. We have a Gibbs equation number 1 here. Reminder that this is the two equations that we use to quantify entropy change, how it relates to other thermodynamic properties for a reversible process. So we have Gibbs equation number 1, equation 6.20. Then simply Gibbs equation number 2, which is equation 6.24 there. That's rewriting equation number 1 and putting our definition of enthalpy. All right. Then we have our specific heats at constant volume. And then our specific heat at constant pressure, equation 1.47 and 1.51. Next, let's do a quick math review here. So specifically, let's look at some expressions of natural log and how we could use those. So specifically, we'll be interested in our second one here, where we have our definite integral from our state 1 to state 2. And we could rewrite that, and that's simply equal to the natural log of our, in this case, internal energy at state 2 divided by internal energy at state 1. That'll be important as you see in our derivations today. And lastly, some of the tables that we're going to be looking at. A reminder, you can get your universal gas constant from the back of your reference manual and also in the back of your textbook. Molecular weights you'll get from tables 1 or 1E. And remember that any table denoted with the uppercase E will be in English units. All right, table 7 and 7E will be ideal gas specific heats of common gases other than air. And so reminder that our specific heats are not constant with temperature when we're using that table. And then finally, table 8 and 8 echo will be our ideal gas properties for air. All right. So we got our math review, our MC311 review. So let's get into the material for today. We're going, as I said, deriving our equations for entropy change, delta S of ideal gas, and we'll be needing to introduce our base equations that we're going to be rearranging for today. And first we'll have our Gibbs equations. And these will be simply rewritten by dividing through by temperature. So we have our Gibbs equation 1 rewritten to be in terms of our entropy change is equal to our change of internal energy U divided by temperature plus pressure divided by temperature T times the differential change in specific volume. And that will be equation 1, and I'll denote each of these equations so we can track it as we go through the derivations. Again, that's just a rewritten form of equation 6.20. Next, we'll rewrite Gibbs equation number 2 for our differential change in entropy. It's equal to our change in enthalpy, dH, divided by our temperature T, minus our specific volume, divided by our temperature T, times our differential change in pressure. And that is equation 6.24. Okay, now we'll use our knowledge of our internal energy and enthalpy change for an ideal gas. So for an ideal gas, I'll substitute I dot G. Remember that our internal energy U is only a function of temperature. So internal energy is only a function of temperature for an ideal gas. And enthalpy, H, is also only a function of temperature for an ideal gas. A reminder that our differential change in internal energy is equal to our specific heat at constant volume times the differential change in temperature. and that is equation 6.29. And that will be equation alpha. Also, reminder that our differential change in enthalpy is equal to our specific heat at constant pressure times our differential change in temperature. And that is equation 6.30. And will be equation Bravo for today. And finally, we're going to be using our ideal gas equation of state and just writing that out for clarity. Our pressure times our specific volume is equal to the universal gas constant R bar times the molecular weight of the gas that we are working with times the temperature. Equation 1.42 and is equation Charlie for our derivation today. All right, so set the foundation here for the 5 equations we'll be using in our derivations to come up with our entropy change of an ideal gas. So let's continue. And if we substitute equation A and C into equation 1, which is our number 1 Gibbs equation, we'll have and also integrate from state 1 to state 2. We'll have our integral from 1 to 2, our differential change in entropy, equal to our integral from 1 to 2 of our specific heat at constant volume times differential change in temperature divided by temperature, plus our integral from state 1 to state 2, the universal gas constant R bar, molecular weight, times the differential change in specific volume divided by specific volume. Okay, and then solving our integral for our change in entropy and applying our knowledge of our natural log for our integral on the right-hand side from state 1 to state 2 of our differential change in specific volume divided by specific volume, we can rewrite this equation into our new form when we have our change in entropy at state 2 minus state 1 equal to our integral from 1 to 2 specific heat at constant volume times the differential change in temperature divided by temperature plus our universal gas constant times the natural log of specific volume at 2 divided by the specific volume at state 1. And we're going to say this is equation 6.32. And remember, we went from this step to here, applying our knowledge that this integral from 1 to 2 of our differential change of specific volume divided by specific volume in this case is equal to the natural log specific volume at state 2, specific volume at state 1. Okay? Next, and then finally, also, we're going to say this is equation 3. Now I will be substituting equation A and B into equation 2 in this case. So let's do that. So substituting equation A and equation B into equation 2. Remember that is our Gibbs equation number 2 from our previous slide. And integrating from state 1 to state 2 on the left and right hand sides, we get this form of the equation. Integral from 1 to 2, specific heat at constant pressure, our different dt divided by T, our temperature, minus integral from 1 to 2, universal gas constant R bar, molecular weight, times our differential change in pressure divided by pressure. And again, simplifying our integral on the left-hand side and our integral on the far right-hand side, applying our knowledge of natural log, we have our final form of this equation, where we have our entropy at state 2 minus our entropy at state 1, our entropy change, equal to the integral from state 1 to state 2 times the specific heat at constant pressure, dt over T, minus the universal gas constant R bar, molecular weight M, natural log of pressure at state 2 divided by pressure at state 1. And this is equation 6.34 and will be denoted as equation 4. All right, so again, we just went from our substituting our equation A and C into equation 1 to get equation 6.32, and substituting equation A and B into equation 2 to get equation 6.34. So this will be our generic form of the equations that we'll use to calculate our entropy change of an ideal gas. Okay, so as I alluded to in the beginning, we said we're going to actually develop a specific equation for entropy change with constant specific heat and entropy change with variable specific heat. So let's talk about why we utilized the constant specific heat assumption back in MC311. And let's look at a graph that's from chapter 1. And you can see how specific heat at constant pressure in this case changes with temperature for different gases. And we're going to be mainly working with air. And you can see how air is pretty constant through the range of temperatures. But if you have a large enough temperature difference, you're going to have a large change in our specific heat at constant pressure, or specific heat at constant volumes, our specific heats. And so we need to make the assumption that we have variable specific heats. And that's why we're going to need to develop our equations for that. If you have enough information about your gas that you're using, and you know that it is okay to assume constant specific heats with little error, we could do so. And so we will also develop our constant specific heat equation for entropy change of an ideal gas. And I'll see you in video 2.